Dear students, in the previous class, we have studied about the crystal lattice and different types of the unit cells. Today, we will study about that how these atoms or the constituent particles are packed in the solid. The atoms are considered as the solid spheres. This is an atom. We consider it as a solid sphere. Now, a matter is made up of atoms. So, how these atoms are arranged in a solid, we will discuss it today. First of all, about the packing in the one dimension. Let us suppose I have so many atoms. Now, how can I pack it in one dimension? Suppose I have so many atoms and I can arrange them this way only, that is in a row. I don't have any other option. So in the one dimension packing, I can arrange the atoms like this. Here you can see this, that this one atom is touching these two atoms and this atom is again touching these two atoms. So the coordination number is 2. What is this coordination number? The coordination number means the number of the touching spheres, that is the number of the nearest neighbors. Here its coordination number is 2 because it is touching these two atoms. So in the single dimension or the one dimension packing, coordination number is 2. You can see the packing in one dimension. The atoms are arranged in one row. Now, the packing in two dimensions. How I can pack the atoms in two dimensions? I have two options. Let me discuss one by one. The one way is I keep the layers in a row in an aligned fashion, and this will be something like this. This is square close packing in two dimensions. It has two dimensions, that is length and breadth. Now let me explain you the coordination number. Just see this ball, this atom, it is touching these 4 atoms. So its coordination number is 4. In the square close packing, the coordination number is 4. Just see the pictures. Can you see a square is formed when we connect or join the center of the atoms which are touching the central atom? That is why it is known as a square close packing. In two-dimensional packing, I have a second option. Suppose if I arrange the second layer in the grooves of the first layer, that is this way. That is this way, you can see that this is the first layer and this is the groove, and the second layer is kept between the grooves of the first layer. So this way I will get a packing like this. This is hexagonal close packing. Why hexagonal? Because when I will join the centers of these balls or the atoms, I will get a hexagon. Just see this ball. It is touching these 6 balls. Now the coordination number is 6. As I have already explained you, the coordination number is the number of the touching spheres. So in the square close packing, the coordination number is 4. In the hexagonal close packing, the coordination number is 6. These are the two patterns how I can arrange my atoms in the two dimensions. Two dimensions means length and breadth. Just see the picture. You can see the balls of the A layer in the grooves of the B layer. A hexagon is formed when I join the centers of the touching spheres. So it is known as hexagonal close packing. Now, if I want to give the third dimension, that is height. Then I will arrange the balls or the atoms above it. Now again I have three options. The first option is, if I keep the balls like this, just above the first layer, or this is my third layer. Now I have the length, the breadth and the height. This is three-dimension packing. Now you can see that when my unit cell will be generated, it will be of a simple kind. That will be a primitive unit cell. This is one way of three-dimensional close packing, and since the pattern of the first layer is repeated, it is known as AAA type. Now the second option, that how can I give a three-dimensional packing a second option, that is, if I keep the second layer in between the grooves of the first layer and again the third layer on the atoms of the first layer. You can see this is A layer, now this is B layer. It is not matching A layer. The B layer is in between the grooves of these two atoms, and then my third layer is again I am repeating this pattern that is at the bottom. So this is AB type packing. Here you can see that the unit cell which will be generated will be of FCC type. I hope you all remember FCC is face centered unit cell that I have told you in the previous class. Now the third option. The third option I have is like this, and layer A, layer B on the grooves of the layer A, this is layer B and this is layer C. The atom is in between the grooves of the layer B. This will be ABC type, and when I'll keep the fourth layer on the grooves of this, the layer A will be repeated. The layer A will be repeated, so this is known as ABC type. In three dimensions packing, I have three options now. I have explained to you. One is AAA type, the other is AB type, and the third one is ABC pattern. This is two-dimension packing, that is square close packing and hexagonal close packing. Now you observe the third dimensional packing, that is AB type or ABC type or AA type. The balls are overlapping the previous layer. Now AB pattern, you can very clearly see that the second layer is on the grooves of the first layer. This is hexagonal close packing, a very close view. Here you can very easily understand the packing from the pictures. Just now you have seen one-dimensional, two-dimensional and three-dimensional packing. In spite of closely packing these atoms, you can very well see these empty spaces. These vacant spaces are known as voids. In the square close packing you can see these voids. Even in the hexagonal close packing you can see this vacant spaces. These are interstitial spaces or the voids. The voids are of two types, the tetrahedral void and octahedral void. The tetrahedral void is a void between the four touching spheres. The tetrahedral void is the vacant space or the unutilized space between the four atoms. These are the four balls, and the empty space enclosed between these four touching spheres is known as a tetrahedral void. Now, the octahedral void, the vacant space between the 6 touching spheres. Now, I am just keeping it this way. The empty space between these 6 touching spheres is known as an octahedral void. Dear children, in spite of the closest packing, the whole space available is not utilized. Some place is not utilized by the atoms and the voids are left. Just have a look on the pictures of the octahedral void and tetrahedral void. Octahedral void is larger than the tetrahedral void, and the number of the octahedral void is equal to the number of the spheres doing packing, whereas the number of the tetrahedral voids is double the number of the atoms undergoing packing. You can see the tetrahedral hole and the octahedral hole. Dear students, I have explained you the packing in the solids, the packing in 1 dimension, 2 dimensions and 3 dimensions. Also, I explained the voids, also known as the holes or the interstitial spaces which are left even after the closest packing. I hope it's all clear to you.